Okay, Miss Mary Elizabeth, this one's for you. You asked me three questions, and the first one I'm going to look at is the alpha, beta, and gamma particles. These are all radioactive particles, so it's going to have something to do with nuclear chemistry. Your alpha particles can have the Greek symbol, looks just like a fish, that's your alpha symbol, and they're always going to show up in a nuclear reaction as a helium isotope. They are the heaviest particles because they have 4 particles in their nucleus, which means they can be stopped by paper, or in our case, our skin, which is why a lot of times you don't hear much about alpha particles because they're so heavy they can't pass through our skin and then therefore don't do any damage to us. If you were looking at a nuclear reaction that said it was potentially going through alpha decay, what that means is I'm going to use an isotope 238, okay, uranium-238, and if it says it's going through alpha decay, remember that decay means to break down. So what's happening is this uranium isotope is breaking down and the decay is an alpha particle. Therefore, it's giving off an alpha particle. And the question might ask you, what's the missing isotope? If an alpha particle is given off, what else? Well, that's where we have to go back to. It started with 92 protons. It has to end with 92 protons. What number plus 2 gives you 92? That would be a 90. What number plus 4 gives you 238? That would be 234. And I do not have a periodic table in front of me, but I really think that that would be thorium. And I would know that because I would have to look up and see who has an atomic number of 90. The next one is the beta particle. And the key thing to remember about a beta particle is that it is an electron. The Greek symbol is simply a capital B, and it definitely has a negative charge because it's an electron. In a nuclear reaction, it's going to have no mass because electrons have no mass. It has a -1 charge. And then, of course, we're going to represent it with an E, or you could also see it represented as a capital B. It can be stopped with aluminum or some of your denser metals, but again, it's simply a fast-moving electron. If we saw something going through beta decay, let's look at again. I have no clue if uranium-238 goes through beta decay, but we're going to pretend it does. If it goes through beta decay, that means it's literally releasing a beta particle. And once again, we'd say, okay, what number goes here so that this number plus a -1 is 92? We put a 91. And at that point, you would look at your periodic table to see who has an atomic number of 91. Again, I don't have one here on me, so I'm not sure. And then what number plus 0 would give you 238? And that would be right there. So our beta particle is an electron, -1 charge, 0 mass. The last one is the one that typically people think of as doing the most damage, and it's a gamma particle. It's represented there with a gamma symbol. It has no mass, no charge, and that's how it's going to look in an equation. Key thing to remember is that it can be slowed down or potentially stopped by lead or concrete. Okay, so that's your gamma particle. The next thing that you had asked me about was half-life. I'm going to go ahead and address that right here. First thing to know is that a half-life graph. If this right here was our isotope, and up here we say that we have something and it's at 100%. The question is, how long does it take to decay to 50%? Okay, because that right there would be the first half-life. So let's say that it's 1 day. If it takes this isotope 1 day to decay to 50%, then the half-life is 1 day. That means on the second day, it's going to go to 25%. And then on the next day, it's going to go to 12.5%. And half-life just keeps getting cut in half. The main thing to understand is that all half-life graphs look the same, and they all have that nice little decrease value. Let's say that I told you something had a half-life of 4 hours. And I tell you that there is a total of 200 grams of this isotope. And then I ask you, how many grams are left after 16 hours? Well, don't complicate this. If you know you're starting at 200 grams, think about what half-life means. Half-life means every time a half-life goes by, 4 hours, what's happening to this number? It's getting cut in half. So after 4 hours, there's 100 grams left. After another 4 hours, what's half of 100? 50 grams. After another 4 hours, half of 50 would be 25. After another 4 hours, it'd be 12.5 grams. And the question asked you how much is left after 16 hours. Well, 4, 4, 4, and 4 is 16. So if the half-life is 4 hours, we started with 200 grams. After 16 hours, we're going to have 12.5 grams left. And that's the simpleness of half-life. Do not complicate half-life. The last one you had asked me about was protons, neutrons, and electrons. I'm going to show this to you two different ways. If you look at your periodic table, and I'm going to use carbon, you see the 6 up here and the 12.011 down here. This number up here is called your atomic number, and it represents the number of protons in any atom whatsoever. So off the bat, I know that it's 6 protons. Remember, if it's a neutral atom, which you're going to assume it's a neutral atom unless it says otherwise, if it has 6 positive protons, it also has 6 negative electrons. To count the number of neutrons, you subtract the atomic mass from the atomic number, and so we would say that this one had 6 neutrons. However, let's say that they give it to you in isotopic notation. Let's say that they give you carbon 14 and carbon 12. And they say, okay, how many protons, neutrons, and electrons does this isotope have? Well, you know it's carbon. So once again, you're going to look at your periodic table and you're going to see, okay, it's got 6 protons, 6 electrons. To find the number of neutrons, you take the mass number 14 minus the atomic number 6, and that's going to give you 8. Okay, so if they give you that isotopic notation, this right here, remember, is the number of protons and neutrons. You know the number of protons is 6, so you're simply going to subtract mass number minus atomic number to get the number of neutrons. Now, let's say that they give you something like calcium. Okay. Here's calcium. Calcium has an average atomic mass of 40.078, and it has an atomic number of 20. And let's tell you that they tell you calcium has a charge of +2. And again, they want to know protons, neutrons, and electrons. Protons is never, ever, ever going to change. It's that atomic number. Now, right here is where things change on the electrons. We see that +2 charge. Remember, if this was a neutral atom of calcium, it would have 20 positive protons and it would have 20 negative electrons. But we see it's not neutral, it actually has a +2 charge, which means it has 2 more protons than it does electrons. So we need to decrease this number, and we would say that it has 18 electrons. And just think about that. If you added a positive 20 plus a negative 18, you would end up with a positive 2. And the neutrons, once again, 40 minus 20 is going to give you 20. I hope that that gives you a little bit of reassurance. You are going to do fine, and please do not stress out about this.